Thank you very much. I thank the organizers for inviting me to speak here. It's a great pleasure to do so and to be here. So I will talk on Bartel van der Waerden, but I start with a slightly more general introduction. Writing the history of a period, in my opinion, can only start when the spirit of the actors begins to loosen its grip on the minds of those who try to take stock of what happened and what it all meant. I am not sure whether the time has come yet to attempt a first account of Grothendieck's language of schemes in a historical context. But I'm fairly confident that the history of algebraic geometry in the 1930s and early 1940s can be attacked today. A very general explanation, which is reasonable, although not covered by old or current usage, of what algebraic geometry is, would define it as the treatment of geometrical objects and problems by algebraic methods. According to this explanation, what algebraic geometry is at a given point in history will then naturally depend on the kind of geometrical objects and problems accepted at that time, and even more so on the given state of algebra. For instance, in Descartes' time, algebraic geometry, in this general sense of the word, consisted primarily in applying the new algebra of the time to problems of geometrical constructions inherited mostly from antiquity. In other words, the algebraic geometry of early modern times was the analytic art of Descartes, Waerden, and others. The discipline which is called algebraic geometry today is much younger. It was created by a process of dissociation from analysis after the Riemannian revolution of geometry. Riemann had pushed the door open towards new objects that eventually gave rise to the various sorts of varieties, topological, differentiable, analytic, algebraic, etc., which happily populate geometry today. After a strong initial contribution by Alfred Klepp...
Impact Lie groups, but... I think what I'm going to do is end 5 minutes early and let you all out.
So this is a subject that goes back a long way, really, to the roots of commutative algebra in invariant theory. Most of you know the history quite well, or at least many of you do. But nevertheless, I thought I would begin by telling you what you might have learned in a first-year graduate algebra class, since that's sort of the right place to start this. Of course, the story starts with Hilbert's proof of the finite generation of the ring of invariance of a reductive algebraic group in the late 19th century. That's the thing that made Hilbert Hilbert, that made Hilbert famous at that time. It was his first big theorem. He was quite a young man, and he was interested in all aspects of this. The one that concerns us here is the question of counting invariance. So, let's see, there's chalk. Hilbert showed, of course, this is prehistory, that if you have a polynomial ring, I'll have standard notation. S will be the polynomial ring over a field K, which I can barely refrain from calling C, in x0 up to xr. And I'll write script m for the maximal ideal, the homogeneous maximal ideal, x0 up to xr. And I'll always think of graded things, graded modules, graded rings, graded homomorphic images of this. And then this prehistory is that Hilbert looked at rings of invariance, things like that, and proved that they were finitely generated by forms of various degrees. He then wrote that sensibly as a homomorphic image of some other polynomial ring whose variables have different degrees, y1 up to yt. And he proved, by a method that I'll show you in a second, that the number of invariants of degree d, the number of independent invariants of degree d, by which he meant the degree d component of this graded object, is eventually a polynomial function of d? Well, a polynomial with periodic coefficients, or more interestingly, he wrote down an actual formula for it in terms of some binomial coefficients. So that's the dimensions of this. Now, that's the prehistory. I want to look at this in a different situation. I want to look at the case where the y's have the same degree, let's say 1. So I'll change my notation and go back to thinking about S and homomorphic images of S. And I want to think of that as a way of getting invariance of projective varieties. Now, we heard from Karen the other day, very elegantly put, that people study families of projective varieties. This is not some wild aberration of the moderns in algebraic geometry. It goes back to the fact that you can write a plane curve as f equals 0, and then you can let the coefficients of f vary, and that's a kind of natural family of varieties. And all the talk about families of varieties since then is a kind of abstraction of the good properties of that example. So, in general, if we look at a variety, I'll think of a homogeneous coordinate ring. So x in PR corresponds to Sx, which will be that polynomial ring there, mod the ideal of x. And these are, again, homogeneous. And a family of varieties would be something like a variety in PR cross some affine space AS, and I think of it as Sx is S with some more variables adjoined for the new affine space, S of T1 up to Ts, mod some ideal I. And then, as Karen told us, x for some point P over there would be just Sx, well, would correspond somehow to Sx mod the maximal ideal of P in these variables. So let's say Sx with the T's equal to T of P. Right, so we take the fibers of the projection of this to AS, and those are the XTs. Now, in our original situation,
the immediate starting point for van der Waerden, who submitted on 14th of August 1925 at age 22 and hardly 9 months after his arrival at Göttingen, an article entitled Zur Nullstellentheorie der Polynomideale, which was published in Mathematische Annalen in 1926. I will show you the opening sentences and some comments on this article in a little while. Let me just end the introduction by taking up the thread I started at the beginning with this definition, the general definition of algebraic geometry, extrapolating just from this bit of the story. A very natural story seems to suggest itself to the effect that what happened to algebraic geometry in the 30s and 40s was a function of new powerful algebra, which was being brought to bear on geometry, transforming this field so as to bring it closer to the algebraic taste of the day. This story clearly, I believe, holds some truth, and it certainly explains van der Waerden's first paper on algebraic geometry cited above, and which I will come back to in a minute. But the goal of my presentation today is to show that this story does not at all give adequate insight into the complicated development of algebraic geometry during the 2 decades, 1926 through 1946. I say 46 because of the publication of the Foundations of André. It is also not the way in which most of the actors or their immediate successors have described the rewriting of algebraic geometry in the 30s and 40s. Consider, for instance, the following quotation by David Mumford from the preface to Parik's biography of Oscar Zariski. The Italian school of algebraic geometry was created in the late 19th century by a half-dozen geniuses who were hugely gifted and who thought deeply and nearly always correctly about their field, but they found the geometric ideas much more seductive than the formal details of the proof. So in the 20s and 30s, they began to go astray. It was Zariski and, at about the same time, they who set out to tame their intuition, to find the principles and techniques that could truly express the geometry while embodying the rigor without which mathematics eventually must degenerate into fantasy. The strong message of this quote is that of a historical continuity and linear progress in the development of mathematics. The injection of new algebraic techniques into algebraic geometry is portrayed by Mumford as a necessary operation in order to save the traditional results collected by the Italian school in order to truly understand them conceptually. Now, while it is true that a number of claims of the Italian algebraic geometry were very much under debate in the period we are looking at, Mumford's account reflects neither the contingency of the way in which algebraic geometry was finally rewritten, nor the considerable complexity of the historical process in which Zariski's and Wei's breakthroughs was embedded. This complexity is the subject of my lecture. Following the sinuous path of van der Waerden's papers on algebraic geometry during the period in question seems particularly suited as a safeguard against undue simplification. So let me now look at van der Waerden. So first of all, how does he get into this? This is so I apologize for the fact that a number of slides are in German and I have not supplied translations, because this talk was first, and the slides were first prepared for the celebration of van der Waerden's 100th birthday in Groningen a few weeks ago. And in Holland, it doesn't pose any problem sort of projecting a German slide and then paraphrasing it in English. I'm sorry, I should have reworked them, but I didn't have the time to do so. I will do my best. This is a letter from Brauer announcing to Helmut Kneser, at the time Courant's assistant in Göttingen, in 1924, that in a few days, he says, one of my students will come to Göttingen for the winter term. His name is van der Waerden. He is very bright and has already published a few things. And then he asks Kneser to take care of sort of formalities that he may have to do with and so on. And in fact, van der Waerden and Helmut Kneser became friends very soon afterwards. Then here is sort of what I alluded to already in the introduction, the very first paper of van der Waerden's on algebraic geometry, and his own account written in English of how it came about. When I studied Emmy Noether's paper, the 23, this is not visible, but it's the 23 paper on elimination theory and general ideal theory, I saw that the point xi with coordinates xi1 through xim was just the generic point I was looking for. So this is cut out of a more general context. I also saw that Emmy Noether's Nullstellenkörper was isomorphic to the quotient field of the residue class ring O modulo P, where O is the polynomial ring K of x1 through xm. Hence, it was not necessary to go through Hensel's elimination procedure. One could start with any prime ideal P, construct the residue class ring in its quotient field, and thus find generic point of variety of P. I wrote a paper based upon this simple idea, showed it to Emmy Noether. She had once accepted it for the Mathematische Annalen without telling me that she had presented the same idea in a course of lectures just before I came to Göttingen. I heard that later from Grell, who attended her course. And this is how he gets to publish, age 22, this paper in the Mathematische Annalen, where he says in the introduction, I just do this first sentence, the exact foundation of the theory of algebraic manifolds in n-dimensional spaces can only be realized through the means of ideal theory, because already the definition of an algebraic manifold leads immediately to polynomial ideals. And then he is proud of having eliminated elimination theory, so to say, in this particular context. So now let us have a quick look at the literature that we are looking at. So the papers of van der Waerden's on algebraic geometry have been essentially collected, edited by Hirzebruch in this volume, van der Waerden zur algebraischen Geometrie, selected papers. This is not as frustrating as the edition of Hasse's collected papers, but still it is a little annoying because a few important papers are not in there. So this is the first page of the table of contents where I add the years, and this is the second page, and I indicate a certain number of things that should have maybe been in there. So what I just mentioned is this very first paper, where he then makes this first and lasting very much lasting contribution to algebraic geometry by defining the notion of generic point in a general satisfactory way, which is later on then used by all the people who follow him, in particular Zariski, as we will probably also hear in the next lecture. After that, there are a few papers here in this list that, if you look here, for example, about multiplicity generalization of Bézout's theorem, which concern the problem, which was actually the 15th problem of Hilbert's problems from 1900, of giving a strict and rigorous foundation of Schubert's calculus of enumerative geometry. So he tackles this, and he tackles this in these first papers still by purely algebraic methods, exactly the kind of algebra that he has also brought to bear on the question of generic point. In fact, his interest in the foundation of Schubert calculus predates his Göttingen days. It appears that he was influenced before he came to Göttingen, when he was still in Amsterdam, by a course given by Hendrik de Vries. But anyway, which was a course on Schubert calculus, and that's how he saw the problem. Now, what happens is that while pursuing this problem and writing a few papers on it, he runs into difficulties. And the first turn, I was talking before in the introduction about the sinuous path taken by van der Waerden in the algebraic geometry. The first turn occurs 1928 through 1932, and it is the paper number 5 here from 1920, published in 29, about the topological foundation of Schubert calculus. So what he says in this paper, so this is the first paper where he sort of contradicts what he said in the first paper. In the first paper, remember, he had said the only exact way to do things is using ideal theory and using that for algebraic geometry. Now he gets another inspiration from Lefschet's method, because I'm not going to go into the technical details, otherwise I wouldn't have time to say what else I want to say, but he just ran in the previous papers into difficulties with this purely algebraic approach, and so looking for help, he turns to a completely different methodological paradigm and comes with a topological notion of multiplicity emulating Lefschet's. This is exactly what he says here. He says, as far as it goes, the algebraic method has a greater generality, of course, than these topological methods, because you can work over any ground field. But if you look at the most general case, sort of having two subvarieties of an ambient variety of complementary dimensions in this ambient variety and try to define their number of intersection, you just hit on problems that you cannot solve in the framework of ideal theory, and therefore he turns to topology. So there is this brief and significant, I think, topological interlude. I also, as you may have noticed, indicate that what happens in his life. So on 6th of May 28, he is appointed ordinary professor at Groningen in the north of Holland, where he was also born, if I remember correctly. But then, subsequently, in 1931, he accepts a job in Leipzig, successor to Otto Hölder, in Leipzig, in Germany. By that time, you should remember, he was already married to Relic's sister Camilla, who is German and who apparently did not like life in Groningen. So there are also personal reasons, but it appears, and okay, so what am I trying to say about this Leipzig job? First of all, this is a little clipping from the letter of the faculty justifying why they want van der Waerden as number one on their list, why they want to hire him, and this is the bit where they talk explicitly about his topological turn in the foundation of Schubert calculus and say how wonderful this is, how good mathematics this is. But in fact, what sort of, as far as mathematics or science is concerned, interested van der Waerden most in Leipzig at the moment of accepting his job was the possible contact with the physicists there, because at that time Heisenberg and Hund were in Leipzig, And van der Waerden was very much interested in this. He gave his inaugural lecture on the group theory as a ordnendes Prinzip. How do you say this? As a principle that, Organizing principle, thank you, and thinking in particular of quantum mechanics. This is when his book on quantum mechanics appears. So it's not so much for algebraic geometry that he wants to go there. So this was the first term. Now comes the second term. The second term occurs in 1932, and this is the way van der Waerden tells the story himself. At the Zurich International Congress in 1932, I met Severi, Francesco Severi, and I asked him whether he could give me a good algebraic definition of the multiplicity of a point of intersection of two varieties of complementary dimension, on which the point in question is simple. The next day, he gave me the answer, and he published it in German, by the way, in the Hamburger Abhandlungen in 1933. He gave several, and so on and so on. So this is the beginning of a new phase and a very important and lasting influence in van der Waerden's work on algebraic geometry. He apparently decides, after having met Severi and after this encounter where Severi proposes this algebraic definition of multiplicity, which I'm again not going to go into, he decides that it is a good idea to try to work together and in contact with Italian geometry, as in particular represented by this towering figure of Severi. And so, for example, there is a letter written by Courant to Tisdale of the Rockefeller Foundation asking for a grant for van der Waerden to go to Rome to, in particular, so he says, Courant says in this letter of March 33, this is a few weeks before Courant will be thrown out of the Math Institute in Göttingen, he says that, in fact, in Germany, the algebraic geometry is practically dead. The tradition is dead, and so we have to refuel it. Now, there were already German scholars, namely Fenchel and Kähler, who have spent some time in Italy on a Rockefeller stipend, and van der Waerden, as a very promising young fellow, should definitely be given the same possibility, and in particular the contact with Severi in Rome will be good for German algebraic geometry or for a collaboration of the two. And van der Waerden himself, in his application, states explicitly that he wants to collaborate with Enriquez and Severi. Severi is the man from which I hope to learn most. Then Tisdale has this note in his diary where he mentions that Princeton wants to get him. These are quotes that I just take from Sigmund Schulze's book. And it is not entirely clear to me why this never came about, whether the Rockefeller Foundation denied the demand or whether the new political situation made it impossible for the Rockefeller Foundation to finance van der Waerden. This is Sigmund Schulze speculates that this was the reason why the foundation didn't give him this grant, but I'm not sure this is the correct interpretation. I think we are lacking some information. So let me remind you of this quote that you have already seen. What we see in van der Waerden's reorientation runs very much against this a posteriori assessment of what happened, you see. Looking backwards, what Mumford says is, well, there were these Weyl-Zariski, and they just had to bring some order to the whole thing. But van der Waerden is exactly trying to do something else. He's trying to collaborate with the main and most productive representative of the Italian school of algebraic geometry in order to clearly bring his knowledge of algebraic methods to the school, but in order to have sort of not a revolution or a complete upheaval or a complete rewriting, but sort of a natural development profiting from all the competence that was already present in the Italian school. So now, how does the story continue? We are actually here now, and I want to talk about what I indicated by this black line. The black line separates those papers submitted for publication before and after the advent of Hitler at power in Germany, the advent of the Third Reich. Now, the very first of these papers does not show any significance, but then the next one this one here, which was submitted on 11th of October 1933, has an introduction which is absolutely surprising. He comments, so first of all, as you probably notice by looking at this, his publications contain in particular that series which is called ZAG, zur algebraischen Geometrie, on algebraic geometry, 1 through, I don't know, 18 or so. And this is number 6 in this series. And he comments now, for the first time, on the goal of this series of publications. He says, the goal of this series of treatises on algebraic geometry is not only to have to find new theorems, but also to communicate or to bring to the readers of the Mathematische Annalen the far-reaching methods and concepts of the Italian geometric school, but with exact algebraic foundations. Then he the apparent goal of this first paragraph is to apologize if he gives a proof of a theorem which may already have been proved in a strict way elsewhere. So he probably it's a safeguard against criticism from the Italian side. Why does he prove this again and not quote my proof that I already gave? So he says, I cannot look for all the maybe correct proofs that exist. I just do my own way. But there is this thing here, which I have underlined in green, where, first of all, he talks about the Leserkreis der Mathematischen Annalen, that is, the readers of the Mathematische Annalen, and then it sounds as if this number of readers there is almost defined with another group of people, namely der Deutsche von heute, the German of today. And that is Nazi lingo. It's very clear in 1933 that if you speak of der Deutsche von heute and of the difficulties of what der Deutsche von heute can understand and cannot understand, you know what you mean. So please don't get me wrong. I'm not saying that van der Waerden was a Nazi. What I'm saying is that he was living in Germany, he continued to live in Germany, and he is picking up, and maybe even picking up more readily than others, because he was a foreigner and had maybe different ears for the German language, the changes in the language environment that there was. And so this, what comes together here is, on the one hand, his interest in collaborating with the Italian school of algebraic geometry, and on the other hand, the political situation in Europe, in other words, the fascist axis between Germany and Italy. And this is what is brought out quite clearly. I jump a little bit just to bring out this point and then turn to other things. In his book that he finally publishes, The Introduction to Algebraic Geometry of 1939. You see, there is a book by van der Waerden, Introduction to Algebraic Geometry. I think it is not at all read anymore today, has been completely superseded by Weiss Foundation first and then what was to come afterwards. And in fact, when you open it, it's very surprising for us. I mean, it looks like Severi almost. I'm exaggerating. It does not at all have the same ring to it as the Modern Algebra had when it came out in 1930. So in the preface of this, he says, this is picking up a thread that I was indicating at the very beginning. He said, I started out from ideal theory, but this ideal theory that I have used in my earlier investigation has now proved to be not necessary in the foundation of algebraic geometry. Instead, it is replaced by the more far-reaching methods of the Italian school. So this marriage between algebra and Italian school is really supposed to be completely realized in this book. And then this is the preface. Then in the introduction, he says that algebraic geometry has arisen from the organic melting of the theory of algebraic curves and surfaces, highly developed in Germany, with the geometry with higher dimensional geometry of the Italian school, and so on and so on. And the reaction to this book is exactly along the lines that I tried to indicate to you. This is the Centralbart Review written by Fabio Conforto. Questo volume, etc. Non si trova invece quel serrato gioco di concetto astratti così caratteristico della moderna algebra che rende quest'ultima di difficile lettura. We do not find in this book those terrible aspects of modern algebra which render modern algebra so difficult to read. That is, he really is an Italian now. He is absolutely even acceptable to Italian geometers. Comunque sia, il notevole libro di Van der Waerden aggiungerà senza dubbio la conoscenza dei metodi della scuola italiana e cooperare ad una reciproca comprensione tra I geometri italiani e gli algebraisti tedeschi. So the goal promoted by this book is friendly and understanding collaboration between, on the one hand, the Italian geometers and, on the other hand, the German algebraists. This is where we are in 39.
By the way, this book was required reading from Matsusaka's students in algebraic geometry in Brandeis.
Which year?
Oh, certainly through 1985.
Okay. Well, okay, so this book was not forgotten, at least not in Brandeis. Okay, I didn't know this. But it does look, you agree, I mean, it does look surprising when you look at it from today's vantage point. So what does all this mean? Well, one sort of warning note I should just sound, and this is a handwritten transparency, just put in there as a safeguard so that nobody will criticize me on that afterwards, is that if you really want to understand what's happening around Van der Waerden in the 1930s as far as algebraic geometry is concerned, you have to look at Severi. That is not easy. There's more than one of the 6 volumes of his collected papers, just papers written in that period. And he is very productive. It is not as if the algebraic geometry only has produced trash in the 1930s. So I know exactly one attempt, sort of more or less historical attempt to at least try to do some justice to this production. That is in this thing here by Ciliberto and Brigaglia, the Italian algebraic geometry between the 2 world wars, where they point out in particular seminal ideas brought forward by Severi, not just going through all the papers, but just sort of classifying curves. For example, the variety V and delta, classifying curves of degree n with delta nodes, or his forthcoming and very rich ideas on different equivalence relation on cycles, which is actually something where a strong collaboration and almost competition arises with Van der Waerden, and Van der Waerden together with his most famous and successful pupil, Chow. So in order to really come to grips with this period, somebody would have to do the enormous job of making a thorough historical study of not only Van der Waerden's papers, as you see them on the left, but also all of Severi's production and see how they mesh together. I have not done this, and it's quite a heroic task, I think, before us. So this was the first sort of brief story I wanted to tell. Now I turn to something else, which, however, is, as you will presently understand, very much related to the story I was just indicating. So there is one other subject, very important in the 1930s, in particular in Germany, which calls for a rewriting or an extension or a generalization of algebraic geometry. And that subject is the Riemann hypothesis for function fields over a finite field, or as we say today, for curves over finite fields. So without going into the technical details, if I try to do this, I would not have time at all to finish my talk. Let me just say that this is an analog of Riemann hypothesis for the L function of such an object, a curve over a finite field. And curves have a genus, and for genus 0, there's really not very much to do. But for genus 1, this is a very interesting theorem, which was proved in 2 ways, actually, 2 different proofs given at a distance of 1 year by Hasse in 32-33, or 33-34 published. And so this is the genus 1 case of the Riemann hypothesis. So after this, the open problem was how to prove the Riemann hypothesis for curves over finite fields for a curve of any genus, higher than 1, curves of higher genuses. And so now I'm going to flip by very quickly, don't be frustrated, some slides with lots of text on them, and I just point out certain things because it's really another story, but I have to run it by you very quickly in order to point out a certain number of things. So the basic idea how to attack this problem was provided by Doering and first communicated by Doering on 9th of May 1936 to Hasse. The idea was, when you look at the proof that Hasse had given in the genus 1 case, you use endomorphisms of the elliptic curve, the genus 1 curve in question. There you have a notion of endomorphism. In higher genus, you don't have endomorphisms. What are you going to replace the endomorphisms with to start doing your proof? You replace them by correspondences. This was Doering's idea. So a theory of correspondences existed, in particular explained in Severi's textbook, Trattato. But of course it existed only over the field of characteristic 0, over C, in this Italian tradition, and so the necessity arose to systematically develop an abstract algebraic geometry which would also work over finite fields, putting up the whole theory of correspondences, proving all the standard theorems, so that then you could deduce from that the Riemann hypothesis, something that the possible strategy was seen immediately by Hasse, as he indicates in his first reaction. Now, Wey comes in because Hasse and Wey correspond at the time. So anyway, I spare you this. There's well, okay, never mind. So Wey, Hasse, Doering, and another Wey, okay. And then this is where I stop. From January 6 through 8 of 1937, Hasse organizes a conference on algebraic geometry in Göttingen. What was the idea of this? The idea of this was to do for algebraic geometry what the Schief Congress that we have heard about the day before yesterday did for the theory of central simple algebras. Remember this congress that Hasse, very young at the time, when was it, 28 or so, organized in Marburg, 31, I'm sorry, still young, 31 organized in Marburg with Brauer and Noether there and so on, where all these developments that we heard about the day before yesterday came from. This was an extremely successful meeting because what did it do? It brought together a small group of the main actors in this field, and they could talk to each other and therefore get to the whole theorem that then was published. And so Hasse had the idea, after this idea of Doering and so on, to bring together all the experts on algebraic geometry. So, well, Doering was in there, there was van der Waerden, there was Geppert, there was Jung, names that you don't necessarily know, but in Germany at that time were certainly considered to be in algebraic geometry and active in this field. He also, Hasse, invited André Wey. He invited André Wey, and André Wey didn't have to think very long. He said, I cannot come, because that's exactly when he was going to Princeton. He was spending half a year, the first half year of 1937 in Princeton, and he already had left Europe before that date. So he couldn't come. The question is, had he not gone to Princeton, would he have considered going? He says in his autobiography that after the Röhmputsch, after May 34, he did not go into Nazi Germany any further than the Black Forest to hike with Siegel. And so if that is true, what he says in his autobiography, he would have never considered accepting this invitation. As it turns out, he didn't have to think about it because he wasn't there anyway. So there is an attempt on Hasse's part to do sort of this, to make this development, and this bringing together of important people, and the same thing continues now in collaboration with the Italian side. Just as I indicated this close contact between van der Waerden and Severi, this generalizes to the Hasse school. So, for instance, there was the famous Volta Congress in 1939. Well, it actually wasn't there. It's one of those congresses I think it's a rare example of a Congress of which the proceedings exist, which has never physically taken place. It was cancelled for some administrative reasons, but since people had sent in their papers, they got published as the atti, as the proceedings of this Congress. So the Congress exists in the form of proceedings. And this was, Hasse submitted to this Congress. He couldn't give it because physically it didn't take place, but he submitted this paper written in it, translated for him into Italian. The goal of which was to sort of teach the Italian geometers the basics of what was needed for the algebraic geometry for curves over finite fields. This was sort of the idea. So to bring these two schools with their respective capacities together. And what about van der Waerden? Well, as I learned from, now I have probably placed this at the wrong place here, this transparency. As I learned just 2 weeks ago, when I was once again sitting in the van der Waerden Nachlass in the archive of the ETH in Zurich, van der Waerden, I can't find it, so I just tell you instead of losing time looking for the transparencies. Van der Waerden received the invitation to this Congress too late. Now, in fact, that didn't matter because the Congress didn't take place, but it was a systematic phenomenon. It did matter because it didn't contribute to the proceedings. But in a sense, it was a systematic phenomenon, and as he tells Hell Braun in a letter, which is in the van der Waerden Nachlass in Zurich, he systematically either received invitation to international congresses too late, so he couldn't go, or if he received them in time and applied to go, he was denied permission to leave the country. So the ministry clearly kept him in Germany. And van der Waerden's interpretation of this is that there was a note in his personal record in the ministry about his participating in the 1934 Congress of the German Math Association in Bad Pyrmont, which was the famous Congress where Bieberbach's attempt to take the whole German Math Association as its new Führer was averted. And van der Waerden was in the anti-Bieberbach camp in that Congress. Another interpretation is possible. This is just the way van der Waerden himself saw it. Maybe, as Günther Frey suggested to me when I talked to him yesterday, it was that the ministry did not like the fact that he never had accepted German citizenship. He was still a Dutch citizen, and maybe for that reason they created problems. Be that as it may, he had problems. He was not allowed to freely exert his international contacts the way he wanted. So now I see that the transparency was right here at the right. Okay, anyway, so I just told you what's in this letter. Well, actually not all of it, but it doesn't matter. So what do we learn from this? We learn from this that in Europe, the most active algebraists interested in algebraic geometry, and in particular I mean by that the Hasse school and van der Waerden, enter into an alliance with the Italian School of Algebraic Geometry and its uncontested leader, Francesco Severi. But this attempt at a collaboration was not as successful as one might have thought or might have hoped, especially if you compare it to what Wey and Zariski realized. The methodological paradigms of the two schools were quite far apart, and institutional and political impediments played a non-negligible role, at least between 1935 and 1945. On the other hand, the two people whom Mumford mentions in this quote and who clearly stand out as those who realized this enormous evolution and development and upheaval of algebraic geometry, Wey and Zariski, did their work and did their foundational work only once they were in emigration. Of course, Zariski left Italy very early. This is probably what Silke is going to tell us in the next talk, so I won't talk about Zariski. But with André Wey, the interpretation that I can give is very clear. As you probably know, regarding the Riemann hypothesis over finite fields, he published an academy note, which he wrote in the prison in 1940, where he claims to have essentially a proof of this, but an essential lemma remains without proof, the positivity of the trace. And in fact, everything that is in this note of 1940 was explicitly present in the discussions in the Hasse School in 1935. Everything. What Weil adds to this, the enormous generalization to give the whole Weil conjectures with, in particular, also the topological part that you, Colin, insisted on so justly yesterday in your talk, plus the whole foundational work that finally, in 46, led to the publication of the Foundations of Algebraic Geometry, all this breakthrough was realized only when he was in the United States. So if you look at it, and I don't think I'm wrong, I mean, it gives the impression that once you liberate yourself also geographically from the presence and influence of the Italian school, in particular as represented by Severi, you can think more freely, and sort of the possibility is there to think of a way of rewriting algebraic geometry which is much more fundamental than what van der Waerden ever tried to attempt during the 30s and 40s. And this, I think, is the reason why van der Waerden's name, much to his own regret, he expressed this several times, also in letters that are in his Nachlass, is not remembered for his contributions to algebraic geometry today, but is remembered for his book Moderne Algebra. So now I will show you a very complicated slide, which I will turn around in many ways, trying to put, this is sort of an attempt one shouldn't make, but anyway, trying to put all the actors that I think are somehow important on one slide. So here you have Severi, which I have mentioned and insisted on. You have, on the other hand, Zariski, whom we are going to hear about, so I'm not going to say anything there. Then I turn around here. You have Gröbner. Gröbner in Germany in the 30s, in a way, is somebody who is very much close in spirit, on the one hand, to the Italian school, on the other hand, to ideal theory. And there is a correspondence in the van der Waerden Nachlass in Zurich between Gröbner and van der Waerden, which almost, I mean, I should be maybe a little careful, especially because this is taped on videotape, but it looks like, I mean, it reads almost like bickering. I mean, it's really, I mean, there are these petty discussions about should one use ideal theory, should one not, and so on, and it's, anyway, so he also published a book on algebraic geometry, but only after the war. Then there is van der Waerden, and I talked about him. I talked about his different periods as far as algebraic geometry was concerned, and mentioned the Chow coordinates as something which is, of course, a lasting contribution, but also linked to the name of his student. There is Geppert, who acts mainly as a translator because he knows Italian just as well as German for the Hasse School. There is Deuring, whose role with the correspondences. So now you see I turn over to the arithmetic side. I mean, with Deuring, I'm already in the arithmetic. These are people who are in the past. Then there is the Hasse School, in particular, as far as this theme of Riemann hypothesis is concerned, with his collaborator H.L. Schmid, who at the time was still in Göttingen, who rewrote practically Deuring's manuscripts in order to make them fit more with the paradigm of presentation of the Hasse School. Then there is Weil, who is, of course, one of the main actors, and I have talked about him. Well, I mean, he has an interest which is slightly different from the German school. Maybe I should say this. I mean, both of them fall under the heading arithmetic approach to algebraic geometry, but the arithmetic approach that Hasse and so on use is more or less directly coming from Dedekind and Weber, I would say, whereas Weil, in his spirit, is somehow more reminiscent of Kronecker, and this is already brought out very early by his 1935 paper on the arithmetic of algebraic varieties, where he implicitly also defines the notion of normalization of of normalized projective variety. Okay, and then the story ends, of course, as is well known, with the 40s. So, but there are other people here on that side of the slide. There is Kähler, who also in this time and way until the 40s, whenever he publishes on algebraic geometry or on geometry, uses the Italian language, not German. There is Helmut Kneser, and then there is somebody I do want to say something about, and he is rightly next to Zariski, and maybe Silke will say something about his role too. That is Krull. I mean, Krull is, of course, an algebraist, as you all know. He has been mentioned before. And he supplies in various papers, for example, it already is indicated in his introduction to his Ergebnissebericht of 1935 about ideal theory, but then more clearly indicated in later papers. For example, in this paper from 1937, he has a very peculiar distinction between multiplicative and additive ideal theory. And by multiplicative, he explains, he means an ideal theory which is sort of directly coming from Dedekind's ideas about decomposing ideals and Dedekind domains into product of prime ideals. And then he will call arithmetical all those approaches to ideal theory and thereby also to algebraic geometry, which are in the spirit of multiplicative as opposed to additive ideal theory. And this is the use of arithmetic, which one finds again in Zariski. This terminology already very clearly shows that Krull had a different approach, did not immediately belong or cannot immediately be counted as a member of the Hasse school. So he is, in my diagram, he is very close to Zariski. He is somewhere else. He is independent in his way of thinking about these things from the others. And even though he stays in Germany, of course, keeping a relatively low profile, I guess, as far, because one really doesn't know very much about it, has direct influence on those actors, Wey and Zariski, who then rewrite algebraic geometry. Okay, now let me return to van der Waerden. Return to van der Waerden in October 1941, so we are now on the next page of the table of contents of this book. So we are here. This is when, at the annual meeting of the German Math Association, van der Waerden gives, as he says, an account of more recent American research on the question of, in this case, desingularization. This is about Zariski's paper, which we're going to hear about. And in particular, the fact that the notion of valuation, Bewertungsbegriff, has played a fundamental role. So van der Waerden is, of course, somebody extremely flexible who immediately picks up on these developments that are realized in the United States and then tries to explain them to the German audience, trying as far as possible to underline analogous work that has already been realized in Germany. So, for example, he quotes Jung and Kneser when he explains Zariski's local uniformization theorem for the resolution of singularities. So he picks up on this, and indeed, he continues to do so. He continues to do so on all sides. This is typical of van der Waerden. So, for example, if you look now just after the war, in 1947, there is one paper about divisor classes in algebraic function fields. So this is somehow a leftover from the war, I would say, in the sense that from his close association with the Hasse school and their attempt to communicate with the Italian school. So he writes his own presentation of algebraic geometry the way the Hasse school liked it to be formulated when dealing with curves over finite fields. On the other hand, that was 47. On the other hand, more or less as soon as Henri Weij's book, Foundations of Algebraic Geometry, comes out, he immediately reviews it. I'm not sure whether this is 48 or 47, but maybe it was printed late. But I mean, it looks like a more or less immediate reaction to the book. Publishes this review in English in the new Archival for Biskunde, and brings out very clearly the points that he likes, the positive points, and is willing to adopt more or less the new viewpoint of proposed by Weij. Not only this review, but he publishes in 1958, that's considerably later, but has the advantage of giving us some idea of how he looked back on all these developments 10 years afterwards. Gives this address about Henri Weij's new foundations of algebraic geometry, which in principle is positive. He just tries to also make some comments about his own findings. Whereas, for example, this is a letter from Hasse to van der Waerden, which is in the Nachlass, where he recommends van der Waerden that he invite to Göttingen Roquette, who has just done in his dissertation an arithmetic proof of the Riemann hypothesis. This was after the war, after Henri Weij had published his proof, whereas Hasse, for example, at this date in 1952 still writes that Roquette's proof is so nice because he, with this proof, you don't have to read this highly complicated book of Henri Weij. So this is not necessarily van der Waerden's reaction to all these developments. I think I have to, oh yes, I already went over time. I'm very sorry. I have to close. Just to recall my basic thesis in what I was trying to defend, it is not a one-way road. And the way it really happened, the way with this sort of sharp rewriting of algebraic geometry realized in the United States, is not alien to the fact that people had to emigrate from Europe and worked in this kind of isolation. Okay, thank you.
Interesting talk, and we are open to questions and discussion.
Just one question on the chronology. When did van der Waerden leave Germany and go to Zurich?
Well, he didn't go from Germany to Zurich. After the war, he went to Holland and lived there under fairly miserable conditions. He worked for some petroleum company for a few years, and then went to Zurich in which year? 1950, right, to University of Zurich. So there was this, he tried, okay, so the story is that the Amsterdam colleagues were prepared to give him a position at Amsterdam University. This was okayed by the faculty, but his appointment, the Queen of Holland refused to sign. So he never got an academic position in Holland after the war.
Olaf?
At one point, van der Waerden was not completely consistent with his Einführung in die algebraische Geometrie, since he uses one of the basic ideas of ideal theory, the ascending chain condition.
And why is this not consistent?
Yeah, in fact, it is ideal theory, what he uses.
Well, I guess one of the points I was trying to make is that van der Waerden, after all, was extremely flexible. And even though I was portraying sort of the way, the style in which the book was written as being very much like the Italian school, of course, in all of his papers through algebraic geometry also, he tries to to write this style, but still supplying the algebraic foundations that he has, of course, up his sleeves. So it is, I mean, okay, he's just...
I think it is consistent because this is sending chain conditions in his first papers. So when you're trying to eliminate elimination theory.
No, what he means...
I'm speaking of the preface or of the introduction to the...
Exactly, because in the introduction he says we don't need ideal theory anymore, but then he uses a bit of it in the book anyhow. Right. In that sense, it's inconsistent.
Do you know how much attention they paid to Van der Waerden?
Well,
for example, this story I told you of Montesquieu. Montesquieu is really a disciple of Weck in some sense.
yes.
And so I wonder how much of this attention to Van der Waerden came from that source.
So I already mentioned one thing, namely that the generic points were sort of taken up by everybody and used, and if when they referred to somebody, they referred to Van der Waerden for this. The other thing, of course, they needed some kind of theory of intersection multiplicities. And one of the authors that he was constantly looking at to trying to get ideas was Van der Waerden, except that in the end he didn't use, as far as I can understand the development, it's not completely clear to me actually. I haven't maybe done all the details in there, but in the end he sort of found his own way to do it. But he certainly was consulting Van der Waerden's papers for this, trying to find inspiration there. And he tried many, many different avenues to come to grips with this essential, but because that's what he needed, the positivity of the...
Do you know what definition Zariski offered back in... Zariski...
definition for what?
Definition of intersection multiplicity. You quoted this.
Severi.
Severi, right?
Oh, Severi.
I
That
missed
was Severi. That was Severi. That was Severi in 1933. Well, I know the paper. I cannot sum it up easily. It's a long winding.
I was struck at what Van der Waerden said about the German of today is that he's not very geometrical, or at least not as geometrical as the Italians. Now, that's not what Bieberbach wanted to hear about the German. I mean, do you think that Van der Waerden was aware of that when he wrote that?
Bieberbach's racist papers begin in November 33. The paper I was showing you was submitted on 10th of October 33. So there was no, I mean, Bieberbach had not spoken up yet in this way.
But apart from Bieberbach specifically, I mean, the German was supposed to be intuitive and geometrical.
I don't know. I don't know. It's just a piece of lingo. I mean, a piece of a formulation that I think was in the air, and which you can actually find in many documents at the time. And I don't think it lends itself